Welcome to the Unit 4, Session 1 of our Financial Modeling course. In this session, we are going to consider the autocorrelation or serial correlation test or serial correlation diagnostics, which is among the further regression diagnostics. In the previous session, we were considering the regression diagnostics, so we considered autocorrelation or serial correlation, but in this session or in this unit, we are going to consider further regression diagnosis. So under this session, we are not only going to look at autocorrelation from the perspective of plot, but we're also going to consider, like in the subsequent sections, we are going to consider the test of autocorrelation as well as other tests of the error term, among other parameters of the financial model or our regression model. By the end of this session, you should be able to explain the concept of autocorrelation or serial correlation. That is the main objective of this session. So, one could ask as to what autocorrelation is, but in our previous session, we have already established, in our previous units or in the previous units, we've been able to establish what autocorrelation or serial correlation is, among others. So, serial correlation has been established that it is not a desirable property of the error term, or it is not a desirable property for the classical linear regression model or the classical linear regression model assumptions. So the fact that this is not desirable or it's undesirable indicate that with respect to serial correlation or autocorrelation, we want to see the absence of it in our series, that is in the error term as well as the explanatory variables. So the error term, or that the error at different times period are correlated, is not desirable. This indicates that if we say that there is autocorrelation or there is serial correlation among the error term, what we are simply saying is that we can predict the error term, which is not the case, because we said that the error term is a random variable or a stochastic variable which cannot be predicted. But if it becomes apparent that we can predict the pattern of the error term, then we are saying that there is also serial autocorrelation among these series. The pattern can be in one of these two forms. That is, it could either be direct. So by direct, we are simply saying that there is a cyclical residual plot over time, or it could also be indirect, which is characterized by an alternating pattern where the residuals cross the time axis more frequently than if they were distributed randomly. Some of the effects of the autocorrelation on the regression analysis are as follows. 1. The coefficient estimate derived using the OLS are still unbiased, yes, but they are inefficient, indicating that they are no longer blue or best linear unbiased estimate, but they have lost the best property due to the presence of autocorrelation. And also the R-square, which is the coefficient of determination, which measures the rate at which the explanatory variables can explain the movement in the regressant or the explained variable, is likely to be inflated related to its correct value. So here we are saying that when there is autocorrelation among or within the error term, there is a chances that the coefficient of determination is going to be inflated, and that the value that we are going to estimate or we are going to derive is not the actual value of the R-square. So there is a chance that we are going to interpret these results based on what we attain or what we derive, but in actual sense they are not what that it is not the case. Since the autocorrelation often occurs in time series data, there's a need for us to employ a regression model which employs time series data or which uses time series data. So we cannot use our previous session analysis because there we had only cross-sectional data. So the issue of autocorrelation is not or does not exist in most cross-sectional data, but autocorrelation is mostly the issue of time series data. So we would like to determine the effect of yearly adjusted inflation. So in our model, we are going to represent the yearly adjusted inflation with IFY, and also we are going to consider petroleum price. These are all time series data. We are going to consider the 91-day Treasury bill rate, which is the risk-free rate that is what we use in the estimation of the CAPM, the capital asset price model. And we are also going to consider TDP, which is total deposit. So in our model, we are going to consider that, or we are assuming that the TDP, which is the total deposit, is dependent on the annually adjusted inflation rate, the petroleum prices, and the treasury bill rate or the treasury bond rate. So these are our parameters, the B1, B2, these are our parameters, and the IFY is the coefficient. So we are going to we are examining as to how annually adjusted inflation, the petroleum price, and the treasury bill explain the movement in total deposit. That is, we are considering the period between July 1990 to September 2020. This is annual data, but they are time series because we are collecting this data over time. So this T subscript, as we saw in the unit 1 of this course, indicate that this is a time series because we have a T subscript indicating that the model is a time series model. So we are saying that the TDP is now dependent on these parameters. So assuming our data is contained in the Bank of Ghana.csv file. So here we are saying that the data that we are going to use in estimating our regression model is saved as a CSV file. That is an Excel file, but this CSV file is a special, a unique way of saving data set, which makes them different from the XLS or the normal Excel file, but still it is an Excel file, but they are saved in a different format. So after we have saved our data set in this, remember we are going to use the eViews application. So there's a need for you to be conversant with the eViews application by this time, because we are going to use this eViews in estimating almost all our analysis in this course. So our regression model will take this form, even now we are considering the time series analysis. So you can also see that this is our regression output. This is our regression output. So in this output we are only seeing we are seeing the total deposit, which is the dependent variable and regressant. So this is the output. That is after you have estimated the regression analysis in your eViews. This is the output we are going to derive. And here we always know deals with the descriptives as I stated earlier by saying that TDP, which is a regressant, and the method is the least squares. This is the sample 1990 to 2020, and there are 243 observations which were included in our analysis. These are the parameters. So we had beta 1, which is the annually adjusted inflation rate, and we have beta 2, which is the petroleum price, and we have the beta 3, which measures the quarterly or 91-day treasury bill rate. So you will see from our observation that even though in this analysis our focus will not be on these results, because we are not seeking to explain these results, but this is also to indicate that this is the result that we had from our estimation, and we are likely going to use these results in the subsequent session to explain as to how there are autocorrelation among these series, or we are going to subject these coefficient or these test results to autocorrelation, because usually we could see that from this analysis we have a coefficient of constant of 5,000, we have a coefficient for the annually adjusted inflation of 5.02, we have PP of 25, our standard error is more than 2 in both situations, our T stat sorry our okay, so in this case we could clearly see that our standard error are higher than our coefficient in the first example, indicating that this is not significant. We could see that with the petroleum price, we could also see that our standard error is less than our coefficient, but our T statistic is less than 2, which also makes it insignificant given the 5% significance level. We also have a probability of more than 6% or 5%, which is 6%, which is also higher than the usual value of 5%. And with the treasury bill, you could also see that there we have the same issue. So this indicate that almost all these estimations are not significant. They are not significant. So we cannot use this estimation in making our decision because most of them are not significant. But we are not focusing on this at this point because we are only focusing or considering our autocorrelation test. So to assess the autocorrelation in the model variables before we can even estimate or before we can even think of subjecting our regression model to the proper or the former autocorrelation test, we can plot the residuals of the regression analysis and see as to how the patterns move, or as whether there are the existence of autocorrelation among the residuals, because our aim is to test for autocorrelation within the residuals. So you could see that there are patterns. So here you could see patterns. There's a trend, unlike the stationary data where you see the up and down movement where you cannot predict the movement. With this one, there is a trend, so one can even depend or rely on this trend to predict the error term, which is not a desirable property. So but given the clear pattern in the plot of the residual, we can conclude there exists autocorrelation, as I earlier said. But the visual evidence alone, this plot alone, cannot tell us as to whether there is autocorrelation or not, because this is not a reliable test. This is just a visual plot, and it could either be the case or not. There could be the points, or there is a chance that there is actually autocorrelation given the patterns in the residuals or the plotted residuals. But there could also be the chance that the graphical evidence could delude us in believing that there is actually autocorrelation, whilst in actual sense there is no autocorrelation. So in the next session, we are going to test for the presence of autocorrelation using a proper or a formal test like the Durbin-Watson test, and also the Bruce-Godfrey Lagrange multiplier test. That is among others. We have also the Lange box test and also the the Pierce box test, which are all used in testing for autocorrelation within the series. But some of the tests can handle higher order tests, and some could also test or handle only lower order tests. But in the next session, we are going to consider the Durbin-Watson, that is the DW test, and also the Lagrange multiplier of the Bruce-Godfrey. In this session, we have learned that autocorrelation is an undesirable property in regression analysis, and we have also considered the likely effects of autocorrelation and assessed autocorrelation using plots. In our next session, we are going to estimate the actual or the formal regression and formal autocorrelation analysis or test or diagnostics using the Bruce-Godfrey test and also the Durbin-Watson test. Thank you for your attention as we meet the end of today's discussion. Hope to meet you once again in our next session.